Good morning, guys. So just to get you guys caught up on where we're at this week, which is really the week before Thanksgiving, we are starting our Work Empowered Lab this week. So just to kind of review what we talked about last week in our videos is um, when we when we have these different molecules, right, like carbohydrates, fats, and proteins, we break them down. Those are all examples of polymers. The individual pieces are monomers, okay? And so, for example, with carbohydrates, the polymer or the larger molecule is known as a starch, okay? The smaller molecule, the individual pieces, we can see these two are the same, is glucose. So we link together glucoses and we get this nice starch molecule. Now, we also learned that with our digestive system, we need to break it down to this glucose level before we can absorb it into our bloodstream. Okay, and so that process usually takes time. It happens in the small intestine. We need enzymes. We start to break down the bonds between these molecules, and then that allows that sugar to enter our bloodstream and go to our cells. Now, one thing we want to think about is when we drink a really sugary drink like pop or Kool-Aid, things like that have a lot of simple sugars. We're really getting something similar to this. Usually, it's two, but it doesn't take very long for that molecule to be absorbed. So as soon as we drink it, it goes through the stomach, then it works into the small intestine, and then all of a sudden it's in our bloodstream. That's why we say, oh, okay, your blood sugar spikes, right? Is because it doesn't take long to digest that at all. Now, if you ate the same number of glucose molecules just in the form of starch, what's going to happen is as you eat that, it's going to go into through his stomach, get into the small intestine, and then we got to break each of those pieces of glucose off. And that takes time, and we break them down. And so one by one, we're letting those glucose molecules go into our bloodstream, so we don't get that spike in blood sugar. So when we're looking at like energy in terms of what type of energy you want, well, if you need like a quick burst of energy, something with simple sugars would be good. But then you're going to crash soon after. If you're looking for long lasting energy, we want to look at starches, right? Because that's going to give you a gradual release of energy over a longer period of time. Okay, and so then we looked at it, and we use carbohydrates as our primary source of energy. Our body wants to break down glucose, turn it into ATP. Fats are kind of the second most. So if we're running low on blood glucose or we're running out of energy, we'll start to metabolize fats. And then finally, proteins. Proteins, your body tries to use those last. So that's kind of what we've been talking about. So basically, the flow is we consume the food, we digest it using our digestive system, okay? And then within our cells, we can convert that glucose into ATP, which is like our body's gasoline, right? So we put gas in our car that makes our car go. And we say gasoline because when you think about gas doesn't come out of the ground as crystal clear, nice, ready to go gasoline, right? It starts out as crude oil. That's like our food. And then we have to refine that crude oil to turn it into gasoline so we can actually use it. Our body does the same thing. We consume our raw, or our not raw foods, but our large foods that then get broken down and refined and eventually turned into ATP if we're going to use them for energy. And that we can use for all sorts of different things, but one of those things is we can use ATP to move. Now, so we're converting chemical energy into kinetic energy. Why is that important? Well, our next lab, the 2.5 lab, is called the Work and Power Lab. So take a minute, make sure we add this to our notes. In science, work is equal to the amount of force applied over a distance. So when we say we're doing work in science, we apply a force, right? And we can measure that in newtons, just like usual, over a given distance, right? So we say, oh, we applied this amount of force for 2 meters, whatever it is. And that's how we calculate work. So if we can't move or if we don't change our distance, we don't technically do work. We can still apply force to an object, but if we don't move it, we did zero work, right? So a practice problem that we talked about in the room is if you had a box, right, and you needed to push that box, and you wanted to push it this direction, and it required we'll say 100 newtons of force. Whoa, there we go, 100 newtons. Okay, and you push that box a distance of 2 meters. Okay, wow, there we go. It becomes a very simple equation, right? So we know that work, whoa, undo that one. That was really bad. We know work equals our force, which was 100 newtons, okay, times our distance, which was 2 meters. That looks like a V, but I'm just bad at writing with this. So it's very easy then. We know that the amount of work we did was 200. And if we look back at that last slide, our unit for this is joules, right? We did 200 joules worth of work there. So that's just something that we worked on. So it's a very simple equation. So now what are we going to do in the lab? Big thing is we started out part one of the lab. You guys, I just want you to go through and do your purpose just like usual. Write a hypothesis, basically saying who's going to have more power, somebody that runs up the stairs or somebody that walks. And then looking at our data here, we want to be able to convert from newtons to pounds. So one thing we talked about is pounds is a unit of weight, and weight is the force as a result of gravity. So weight is actually a force, and we can measure that in pounds. Newtons, we talk about measuring force. So these are force, but we need to be able to convert between the two. So what we did is we used this nice fancy spring scale, and we'd pull our, let's see if I can do this for you guys. We'd pull the spring scale down to 1 Newton, okay? And then we looked on the back and said, okay, that's equal to 100 grams. And then we know there are 500 or 454 grams per pound, and we were able to convert and get this amount of pounds per each Newton, okay? So we kind of went through, I'm just gonna give you guys these. You don't have to convert that, but that allows us to understand, okay, if we have this many Newtons, that's this many pounds. So this part kind of walks you through it. Now, the analysis portion, we want to graph this, okay? And when we graph this, we want to have newtons on our y-axis, okay? And we're going to have pounds on the x-axis. And so when we think about this, this one's pretty easy because we got 1, 2, 3, 4, 5 newtons is what we went up to. These data points, let's just use that decimal that we found. So 0.22, 0.44, 0.66, 0.88, and 1.1, okay? And when we do that, we get a nice line that looks like this, okay? So when we find the slope, just like in math, we got to take 2 points and we go rise over run, okay? And it doesn't matter which 2 points you use, but what we found out is that our rise is 1 and our run is 0.22, okay? And now 1 over 0.22, that's kind of a slope, right? We don't want to do that. But if we do 1 divided by 0.22, what that gives us is actually 4.5. Ooh, there we go, 4.5 over 1. That's a much better slope. And when we actually look at what this means, we had newtons on the y-axis, which means there are 4.5 newtons for every 1 pound. Okay, so that is when we ask what the conversion is between pounds and newtons. We know there's 4.5 newtons for every 1 pound. So now when we convert our weight, we simply say, okay, Mr. Harthen is Big Chungus, and he weighs 175 pounds. Okay, and we're going to multiply that by 4.5. Okay, and that will convert my weight from pounds into newtons. Okay, so that's basically what we did there. So where are we going to use this? On the next part, what we're doing today is we are going to be running up the stairs, and we're going to be able to say how much work did we generate. So what you're going to do is you're going to take your weight in pounds. If you don't want to tell me your weight, I don't care. Choose a weight, convert it to newtons. The height of the stairs is about 15 feet or this many meters. Okay, and we're going to calculate the amount of work done in foot pounds and in Newton meters. Okay, and then let's say our average time was 7 seconds going up the stairs. So as you go through this, when we get down to here, it walks you through the calculations on how to calculate work. And when you do that, you're just going to plug that into your data table here for both foot pounds and Newton meters. Then it also tells you how to calculate power, okay, or horsepower. This is really step C, okay. or foot-pounds per second is horsepower. When we look at watts, now it is Newton meters per second is a watt. So we can calculate our power rating. So we learned that power is work over time. Okay, so that's kind of what we're going to be taking notes on today. So just make sure you take a second and pause the video and write this into your notes today. So that's basically what we're doing. And then when you get down to the bottom, okay, we should be able to answer our synthesis questions here, like how are work and power related, and then what is the energy source that we used in this lab. Okay, if you have any questions, let me know. Okay, bye.